Hello, welcome to another episode of the Stupid CS Guy. We are going through Amazon Dynamo Paper. Our intent is to understand what goes behind building a highly available key value store. Incidentally, a highly available key value store is also a very common problem in system design. With that, let's jump in. In the previous episodes, we covered partitioning, consistent hashing, spoke about vector clocks and reconciliation, and we also spoke about how Dynamo makes the writes durable as well as highly available. Just to recap a bit, the most important part of the previous episode was the understanding of three numbers R, W, and N. N is the number of nodes in which your writes are copied. Then there is the concept of R. So R is the minimum number of nodes that must participate in a successful read operation. That means if you set the R to 5, the coordinator node is going to wait for all of those 5 nodes to send back their data before replying. If there are inconsistencies in that data, then of course they'll be reconciled and they can be sent back to the client, but the client can also reconcile. You have to have an optimum R because keeping the R really large would actually slow down the system and violate the latency requirements that we have of Dynamo. Similar to R, we have W is the minimum number of nodes that must participate in a successful write operation. So this is important. What is the difference between W and N? W is the minimum number of nodes that must participate in a synchronous write operation. So if your W is, let's say, 5, it will wait for all 5 nodes to commit the update before returning a success to the client. You can see a trade-off. Keeping the W too high is gonna violate the latency requirements that we have of Dynamo. Setting R and W such that R plus W more than N is a quorum-like system. This is super important. We spoke about it in the last part. I'll suggest if you have not done that, go see the last part. In this part, we are going to talk about handling failures. What happens when there are failures in a distributed system? For example, there can be temporary failures where your system restarts or some box goes down and comes back up. These are very normal. The system we design in a distributed system should take care of these failures. So if Dynamo used a traditional quorum approach, it would be unavailable during server failures because you would need all the nodes to be available. To remedy this, it does not enforce strict quorum membership and introduces a sloppy quorum. All read and write operations are performed on the first n healthy node. So it does not mean that all the nodes which have your data needs to participate. It just needs n nodes to participate. The first n healthy nodes to participate in a read or write operations. So consider the example of Dynamo configuration given in figure 2, which I have here. In this example, so the key comes and gets stored in A, and let's say n is equal to 3, which means it gets stored in A, it gets stored in B and C. If this example, if node A is temporarily down or unreachable during a write operation, then a replica that would have normally lived in A will now be sent to node D. And instead of having a change in A, the change will now get propagated to D. This is done to maintain the desired availability and durability guarantees. The reason being we have set the n equal to 3, which means our data needs to be copied into 3 locations, and that is why it is being copied over to D. But the replica sent to D will have a hint in its metadata that suggests which node was the intent recipient of the replica. So what is happening is key comes in. Normally we know that the K key belongs to A, but A is down. So it goes top end nodes B, C, and D. The D will have a hint saying that, hey, this is not something I generally own. I am keeping this temporarily till A comes back. And when A comes back, I'll send the data to A. So this is called hinted handoff, where the replicas have hints saying that this data belongs to somebody else. Nodes that receive hinted replicas will keep them in a separate local database that is scanned periodically. Upon detecting that A has recovered, D will attempt to deliver the replica to A. Once the transfer succeeds, D may delete the object from its local store. So using hinted handoff, Dynamo ensures that the read and write operations are not failed due to temporary node or network failures. A can go down, A can restart, does not matter. As long as you have machines in the cluster, your data will get saved in one or the other machine and it will go to its correct machine whenever that machine comes back up. So another important point here that a highly available storage system should be capable of handling the failure of an entire data center. Now this might seem very weird and improbable, but this actually happens. Think of in the case of a tsunami. Recently Microsoft's Azure data center was affected because of a lightning strike. So you have the natural calamities that can bring a data center down. There could be other cases where there's a cable cut that brings the data center down. Granted that this is a rare phenomenon, but you do not want your business to come to a stop because one of the data centers went down. Dynamo is configured such that each object is replicated across multiple data centers. In essence, the preference list of a key is constructed such that the storage nodes are spread across multiple data centers. Of course, that means added latency. These data centers are connected through high-speed network links. This scheme replicating across multiple data centers allows us to handle entire data center failures without a data outage. So hinted handoffs is how we handle transient failures. When a node is restarting, another node serves the request, keeps a hint that it needs to give it back to the original owner. That's what hinted handoff is. But what happens when there are permanent failures? Let's say the entire disk went for a toss or the system just failed and was not coming back. Hinted handoff works best if the system membership churn is low and the node failures are transient. Why it works best if the system membership churn is low? Because all nodes know that where does this key belong. So the information that they have about the membership is up to date and hence hinted handoff works best in those cases. Now for permanent failures, the only way to handle this is to replicate data as fast as possible to other nodes. Now to do this, Amazon Dynamo uses something called as Merkle tree. So just let's read through this. To detect the inconsistencies between replicas faster and to minimize the amount of transfer data, Dynamo uses Merkle trees. So think about you have two nodes and you're replicating in from one node to another node. How do you know that data in one of the nodes have changed and that needs to be replicated? And the way they do it is through Merkle trees. So let's understand Merkle trees. These are two nodes which store data. So you have node 1 which is storing the data, it is one of the top end nodes, and node 2 which is another of the top end nodes but comes in at a later priority, which is also storing the data. At every once in a while we are going to periodically sync all the nodes. So think about the node 1 having bunch of these keys. In normal cases, node 1 would have to say that, hey, this is what my values of keys are. Let's just make sure you also have the same thing. You will have to send a large amount of data through the network, and also it's going to take a lot of time. So instead, what Dynamo does is Dynamo just checks the hash of the root. So what Merkle trees do is, so you can see X, W, X, Y, Z are the data that gets stored here, and each of the nodes have its hash stored here. W and X with the leaf hash, we create a combined hash of the parent node. And then again from those we go up above and we create a combined hash of the root node. So the first thing that the node 1 and node 2 needs to do is to make sure that if the root node matches. If the root node matches, it means the entire tree matches. There is no other data needs to be sent. So you can see that it's just an exchanging of hash that needs to be done and it is super fast. Now let's say they don't match. The next thing node 1 does is says that, hey, this did not match. That means there's some change. Let me give you my left subtree and the right subtree hash and send it to node 2. Node 2 checks that, hey, the left subtree is matching, the right subtree is not matching. So that means the difference is just in the right subtree. And then we start going deeper. So we go through each node, figure out if the hash changed, and then only synchronize that portion of the data. We do not synchronize the entire data that you have in node. So that makes it super fast. A Merkle tree, like we said, is a hash tree where leaves are hashes of the values of individual keys. For instance, if the hash values of root of two trees are equal, then the value of leaf nodes in the tree are equal and the nodes require no synchronization. That makes it super fast because with just a small amount of data, we are able to guarantee equality. If not, it implies that the values of some replica are different. And in case the nodes may exchange the hash values of children, and the process continues until it reaches the leaves of the trees, at which points the host can identify the keys which are exactly out of sync. So Merkle trees minimize the amount of data that needs to be transferred or synchronization and reduce the number of disk reads performed, thus speeding up the entire process. Next, let's come to the membership and failure detection. Now, in Amazon's environment, node outages are often transient but may last for extended intervals. This is very common in all data centers. First of all, there can be a small cable cut, there can be a temporary failure in a cooling system, or something where it could be transient but may last for extended intervals. A node outage rarely signifies a permanent departure and therefore should not result in rebalancing of the partition assignment. Now, rebalancing is costly. That means you are saying that these keys will stay in these machines and you need to rebalance it across the cluster. Similarly, a manual error could result in the unintentional startup of new Dynamo nodes. For these reasons, it was deemed appropriate to use an explicit mechanism to initiate the addition and removal from the Dynamo ring. So you have this ring of machines. What people is trying to say is that sometimes these machines can go down, but we should not be worried because these machines will come up at some other point in time, so we do not want a full-on rebalancing of the ring. The administrator uses a command line tool or a browser to connect to a Dynamo node and issue a membership change. So without this trigger, a membership change would not automatically happen. The node that serves the request writes the membership change and its time of issue to persistent store. The membership change forms a history because nodes can be removed and added back multiple times. In some database systems, you have something like a zookeeper which keeps the membership history. So zookeeper is a central list of servers which keeps the membership information of the cluster, which key belongs to which machine. For Dynamo, we decided that we will not have this single point of failure. Instead, all machines should equally share the data. And that is what this paper is saying. Dynamo uses a gossip protocol to propagate the membership changes across all the nodes, which means that all nodes will have membership informations. All nodes know that this key is present in this machine. And how does it do that? So gossip protocols are which maintain relaxed consistency requirements amongst a very large group of nodes. It's a simple concept. Each node sends out some data to a set of other nodes. That's all it is. Data propagates to a system node by node like a virus. So you have you talking to your neighbors and then neighbors talking to other folks, just like how WhatsApp forwards happen. It is exactly how fake news propagates. Somebody tells their neighbors tells other people, and before you know it, everybody has that fake news message. So eventually data propagates to every node in the system. It's a way for nodes to build a global map from a limited local interactions. So each node's contact appears chosen at random every second, and the two nodes efficiently reconcile their persistent membership change histories. So the partitioning and placement information also propagates via the gossip-based protocol, and each storage node is aware of the token ranges handled by its peers. This allows node to forward a key's read-write operations to the right set of nodes directly. Now you might rightly think that you have so many machines in the ring. Can there be partitioning? Can it happen that a set of nodes talk to each other and another set of nodes talk to other nodes and they don't know about each other? And it could temporarily result in a logically partitioned dynamo ring. For example, administrator could contact node A to join A to the ring, then contact node B to join B to the ring. So you have two machines getting joined in the ring. But in this scenario, node A and B would each itself consider to be themselves to be a member of the ring, but they're not aware that of each other. B does not know that A is member of the ring. Now, to prevent logical partitions, some dynamo nodes play the role of seeds. Seeds are nodes that are discovered via an external mechanism. So, for example, a load balancer out of the system. The idea is that the seed nodes are kind of the gateway to the cluster, and all nodes eventually reconcile their membership with the seed. So, logical partitions are highly unlikely. So, what happens when A and B joins? They find a seed which is C, and they reconcile their membership with C. and hence you will not have logical partitions. So the failure detection is also decentralized. A purely local notion of failure detection is entirely sufficient. Node A may consider node B failed if node B does not respond to node A's messages. In presence of a steady rate of client requests generating inter-node communication in a Dynamo ring, a node A quickly discovers that node B is unresponsive. Decentralized failure detection protocols use simple gossip style protocol that enable each node in the system to learn about the arrival or departure of the nodes. Because think about each node is talking to each of their neighbors, so any change quickly propagates throughout the ring. Now, this part talks about the implementation. We have gone over the hard design decisions part. On the implementation side, it's very straightforward. You have a request coordination, you have a membership and failure detection, and a local persistent engine. And the Dynamo engineers have all of these written all of these components in Java. Now let's look at what exactly happens when a read request comes. So of course Dynamo sends the read request to the nodes. It waits for the minimum number of required responses. This is what your R value is. If too few replies were received within a given time bound, fail the request. Otherwise, gather all the data versions and determines the ones to be returned. So the larger your R is, the greater chance of one node going down and that affecting your request. So that is why you have to optimize R so that you have a good balance between durability, consistency, and availability. And if the versioning is enabled, because the read fanned out to multiple nodes, if the versioning is enabled, perform syntactic reconciliation and generate an opaque write context that contains the vector clock that we spoke about in the last lesson. Experiences and lessons learned, business logic specific reconciliation. Now, this is a popular use case for Dymo. In case of divergent version, the client application performs its own reconciliation logic. Generally, we think when a key has two different values, we will choose either or one, right? That's our intuition. But for Amazon, especially the cart, it could be a merge operation where the business logic can reconcile objects by merging different versions of a customer's shopping cart. So this concept of vector clocks really helped Amazon. High performance read engine. Now, while Dynamo is built to be an always writable data store, a few services are tuning it to its quorum characteristic, using it as a high performance read engine. Now, how are they doing that? Remember, we have three parameters we can control: R, W, and N. What these services are doing is they're setting R to 1. That means they're not waiting for two machines to reply. Instead, just waiting for one machine to reply and they're okay with it because the amount of writes that they handle is less. So the chances of conflicts are also much less. So in this configuration, typically R is set to be 1 and W to be N. For these services, Dynamo provides the ability to partition and replicate their data across multiple nodes, thereby offering incremental scalability. Now, the main advantage of Dynamo is that its client applications can tune the values of N, R, and W to achieve the desired levels of performance, availability, and durability. If there is one thing you take out of this video, this should be it. For instance, a value of N determines the durability of each object. A typical value of N used by Dynamo's users is 3. Now, Dynamo really tries to eke out as much as performance from the system as possible. And one of the optimizations that they did was in the optimization, each storage node maintains an object buffer in its main memory. Each write operation is stored in the buffer and gets periodically written to a storage by a writer thread. So what it's saying is when a write request comes through, the node just stores it in its memory and immediately returns, thereby making it super fast because the node is not waiting for the data to be written in the disk. But then this has its problems. Yes, is a durability risk, and Amazon knows that. What if like you've stored it in memory and the machine restarts? To reduce the durability risk, the write operation is refined to have coordinated choose one out of n replicas to perform a durable write. A durable write that is that a direct write to the store. Since the coordinator only waits for W responses, remember the coordinator waits synchronously for only W responses. It does not wait for all N machines to commit the write. And most of the machines are just committing the write when they put it in memory. So one of these machines of course, will take a little more time, but that's okay because coordinator will only wait for W response and immediately send an ACK. So the performance of the write operation is not affected by the performance of the durable write. This is based on their thinking that you have so many machines in the cluster that not all of these machines will go down at the exact same point in time. So even if you have an asynchronous write into the disk, it is fine. If you have seen my previous video, you would know that Dynamo uses vector clocks to track the versions of each of these values. Now, how much can they diverge and how many can it be? So divergent versions of a data item arise in two scenarios. The first is when the system is facing failure scenarios such as node failures, data center failures. That means it wrote into one node, it was not able to write into another node, then something else happened and that node was overridden, so and so forth. And the second is when the system is handling a large number of concurrent writers to a single data item. The number of concurrent updates to one value is so high that it is going in multiple other machines in a short period of time and they are not able to reconcile. From both usability and efficiency perspectives, it is preferred to keep the number of divergent versions at any given time as low as possible. You do not want 10 versions of your card. Reconciling them is going to be very, very difficult. If the versions cannot be syntactically reconciled based on vector clocks alone, they have to be passed to the business logic for semantic reconciliation. That is where the client or the business logic reconciles and creates the modified cart. In the experiments, the number of versions returned to the shopping cart service was profiled, and 99.94% of requests saw exactly one version. Only a very low percentage of requests saw two versions, and even lower saw three, and very negligible percent of requests saw four versions. This happens rarely. And what Amazon says, it is not by users, it is triggered by busy robots. Now, the last part here is client driven or server driven. Any Dynamo node can act as a coordinator for a read request because all of these Dynamo nodes know which key is present in which node. Write request, on the other hand, will be coordinated by a node in the key's current preference list. The key is stored in three or four nodes. One of those nodes should handle the write request. One of the ways that you can have request coordination is that client requests are uniformly assigned to nodes in the ring by a load balancer. So the load balancer also knows about the membership. For read, it assigns to anyone on the ring. For write, it assigns to the correct machine. An alternative approach to request coordination is to move the state machine to the client nodes. In this scheme, client applications use a library to perform request coordination locally. So the client directly reaches to the concerned machines instead of going through a load balancer. Just think about, you have this Dynamo instance where one aspect could be where client sends the request to load balancer. Load balancer knows where this write data is present. So load balancer talks to the actual machine. And of course, this then coordinates however it can. So you have this one extra hop here. What if the client, when it connects, client also gets this map saying that this key is present in this data store, and client directly connects here instead of going through the load balancer. So instead of the load balancer, the client directly connects to the machine. So using this information, client can determine which set of nodes from the preference list for any given key because the client library contains the Dynamo membership state. With that, they have profiled and they have figured out that the latency for client-driven architecture is of course smaller because you avoid one hop. This is Dynamo trying to eke out as much performance benefits as they can out of the system. Obviously, this has some downsides. The efficiency of this scheme is dependent on how fresh the membership information is at the client. Currently, client polls a random Dynamo node every 10 seconds for membership updates. With that, we come to the end of the Dynamo paper. I hope this was helpful. Like I keep saying, if there's one thing that you need to take out from this entire series is how Dynamo provides the necessary knobs using three parameters, N, R, and W, to tune their instance based on their needs. All of those comes with trade-offs. We spoke about cap, we spoke about tassel. In essence, making a large-scale distributed system like Dynamo is allowing users to do their own trade-offs. And lastly, the production use of Dynamo for the past year demonstrates that decentralized techniques can be combined to provide a singly highly available system. From the external point of view, it looks like a single system, but it is a decentralized system. Its success in one of the most challenging application environments shows that eventually consistent storage system can be a building block for highly available applications. With that, this series ends. I hope this was useful, and I would love to know your feedback and if you have recommendations on what should I cover next. Please like, share, and subscribe. Thanks.